Morning, everybody. It's an honour to help open the meeting. Pleasure to be back in Liverpool, back with the Challenger Society. Lovely to see some friendly faces in the audience. As the theme of the meeting's oceans and climate, I felt compelled to talk about some of my work and work with colleagues on the possibility of abrupt climate changes, or so-called climate tipping points, especially the role of the ocean in those, and the possibility that we might actually be able to get early warning signals before we reach a climate tipping point or trigger abrupt climate change. So I want to say a little bit about what do I mean by climate tipping points, what are they, and then get on to do they carry early warning signals and what are those, giving some ocean examples throughout, and if time permits, a little bit about recent work on what should we be doing about them, how should this be changing our approach to the climate change problem. So our old friend, the thermohaline circulation and its Atlantic component, the Atlantic meridional overturning circulation, is going to crop up quite a lot in the talk. But for the more biologically orientated in the audience, I've also tried to give something for you in the middle, as you'll see. But in terms of the physical climate system, the thermohaline circulation and the Atlantic part of it is a key part of the climate system, as well as being a key aspect of, or perhaps the key aspect of the long-term ocean circulation. The northwards transport of heat, especially in the Atlantic sector, is dragging the band of rainfall in the tropics around the planet, called the Intertropical Convergence Zone, northwards. And as we'll see in a minute, if the overturning circulation of the ocean changes, the rainfall patterns all around the tropics change as well. And the thermohaline circulation has been kind of the poster child of abrupt climate change for decades now, because of the recognition that there could be an alternative stable state for this circulation where the overturning in the Atlantic sector at least is essentially switched off, and that's also stable for a range of kind of global climate boundary conditions. So that would make the thermohaline circulation, or the Atlantic meridional overturning circulation at least, an example of a kind of system that can have two different stable states for a range of what's on the x-axis there as climate forcing, or sort of global climate boundary conditions. So we know the overturning circulation switched on, transporting warm water at the surface northwards, sinking in the high northern latitudes with a return cold flow at depth. But the sort of no overturning circulation off state can also be stable for a range of climate boundary conditions in a range of models, and as we'll see, we think switches between these states have happened in the past. Now, one kind of conceptualization of what it would mean to pass a tipping point would be the idea in that example that you could force the overturning circulation in a way, perhaps involving adding extra fresh water to the regions of the North Atlantic around Greenland. You could force the system in a way that its current state of overturning circulation could lose stability, and that's what the tipping point represents here, where that bold line kind of runs out. And then the system is a kind of forced to undergo a transition into a different stable state that already exists, which is the off state down here. Now, this kind of cartoon can be applied to other bits of the climate system. For example, the volume of ice on Greenland or West Antarctica, but I'll keep coming back to the ocean example. To make it a bit more visible, I was going to try and run a movie of the tipping, which I can see is not playing ball. It was working 2 minutes ago, well, 10 minutes ago when I tried it, so that's upsetting, isn't it? Let's hope the next movie when it appears. Oh, here we go. Okay, so now I'm kind of got a cartoon of this system. I actually started it a bit further back, but I'm forcing the system in a way that it's going to tip out of this. This state is losing stability and it's going to tip out of it in a minute. And we're subjecting the system to what I'll call noise, a little bit of fast timescale perturbation, if you like, which for the ocean could be just thought of as the atmosphere and the weather and the faster dynamics of the atmosphere. And you saw cartoon just there of the system passing the tipping point and going into this alternative basin of attraction. Now, when we look back in Earth history, we see dramatic changes, even just during the last ice age cycle. Here in the blue, it's a proxy for temperature in Greenland, but in the red and the green, these are actually marine sediment proxies for essentially rainfall in large catchment areas of big monsoon systems in the Amazon, northern South America, and in India. So in the blue, we see a series of abrupt warming events, famously known as the Dansgaard-Oeschger events. Over 20 of these abrupt warming events are seen in Greenland. The ones we can resolve really well happen within 5 years or 10 years certainly, and might involve 8 degrees of warming in Greenland. And they're understood as certainly involving a key role for abrupt shifts in the Atlantic overturning circulation as coupled to the atmosphere and the sea ice. But as you can see, when there are big jumps in the North Atlantic region, the consequences are just not isolated there. There are correlated shifts in the monsoon systems around the tropics. And that's because with major shifts in the overturning circulation in the Atlantic sector, we're shifting this band of rainfall around the planet, the intertropical convergence zone, with it. Northwards if the circulation is getting stronger, or southwards if it's getting weaker. So hopefully that gives a flavour of some of the role of the ocean in the interconnected climate system and in abrupt changes. I've been spending a lot of the last 10 or more years trying to map out what are the bits of the climate system that might be able to exhibit alternative stable states and that might conceivably be tipped between them, thanks to human activities, in particular this century and next. And there's lots of stuff on the map is one thing to take away from it. There are things in red that involve circulation change, including changes in the thermohaline circulation, but also these monsoon systems in India and in West Africa. There are things there in blue that involve essentially some systems involving the melting of ice, like major ice sheets. And there's things in green which would be the possibility for abrupt shifts in major biomes. Of course, we might not have got this right, and this is kind of a work in progress map, but and I try to keep updating it. But the key message perhaps is there's quite a lot of bits of the climate system that may have the possibility to pass tipping points. We would love to know how close those tipping points are, especially if they get more likely as the temperature goes up. This is a kind of sketch of that I would have drawn more than probably around 10 years ago. And as you can see, at that time, we put the prospect of tipping the Atlantic overturning circulation as one of the more distant tipping points. In the intervening decade, we've learned some things about the weaknesses in our models, and some would argue at least that our models are kind of biased too stable, and we might be a little overconfident in how far away a tipping point for the overturning circulation is. But then at least it was thought you needed sort of high-end warming, 4 or 5 degrees warming within a century to tip that circulation, whereas other systems, especially in the Arctic, could be much nearer a threshold. And we've learnt since, for example, that we can't rule out that the West Antarctic ice sheet is already, or at least a large sector of it, in a kind of irreversible retreat or shrinkage. Another way we might, of course, figures like that come from trying to kind of do some modelling work myself, but mostly assimilate the literature on our current kind of best model-based understanding. But there's always weaknesses in models, as I've just been hinting. And another way you might try to get a handle on, well, how likely are these tipping points or not, is to ask some experts on particular bits of the climate system in the hope that the experts know something about the weaknesses of their models and can kind of bring that into their assessment. So this is a pretty complicated figure, I'm afraid, but it essentially summarizes an expert elicitation process where a series of experts are asked if they feel confident in their knowledge on a particular system to give a kind of likelihood of tipping that bit of the climate system under either low warming, which is less than 2 degrees, medium warming, 2 to 4 degrees in the year 2200, or business as usual high warming, which is there 4 to 8 degrees in 2200. And each of these bars is an individual expert giving a imprecise probability range on the likelihood of tipping a system. Essentially, you can see some kind of intuitive things, like as the temperature goes up, the likelihood of tipping systems tends to go up. Looks like the threat to Greenland, at least when the elicitation was done, was seen as greater, if you like, than the threat of collapsing the overturning circulation. But even for our Atlantic system, when we get to high warming, a kind of aggregation of the expert probabilities, which is the coloured bit, would put it as kind of as likely as not that you might tip that system. You can then do some complicated work to try and conservatively kind of set a lower bound on the probability of tipping any one of these systems by kind of combining the expert responses. And even with the most conservative assumptions, the headline message is, if we carry on business as usual, the sort of red scenario, then tipping point becomes more likely than not. And I'm mentioning that because at the moment in our assessment of the economics of the climate change problem, we typically assume that these are high impact but extremely low probability events, whereas this round of experts at least say that these are both high impact and, if we carry on business as usual, high probability events. And that should be changing our perception of the climate problem, and I'll try and come back to that at the end. But before that, let's get on to early warning, because many of you may share reservations with me about, the merits or not of asking a load of experts the likelihood of certain systems being tipped. So it'd be nice if there were some direct information we could get on that. And of course, ideally, we would trust our state-of-the-art models and run them forwards under realistic forcing and wait to see if and when something dramatic happens. But I've been kind of curious about the possibility that there are maybe direct signals from data that a system might be approaching an abrupt shift. So the idea here is coming from a quite well-established bit of mathematics in so-called dynamical systems theory. We've got the same cartoon I kind of showed earlier of a system being forced in a way where its current state loses stability and then it has to roll off, if you like, into the other state. But I've drawn on there a kind of radius or curvature of they're called the potential well the system sits in physics. And the radius of that well, or the curvature, is related there to a tau, a time scale. And that's literally the time scale that a system recovers here from perturbations. So the basic idea is, as a system approaches a tipping point, perversely, although it's approaching an abrupt shift, its recovery from sort of short-term fluctuations should get more and more sluggish, slower and slower. So a system should actually slow down in its response to nudges before it's coming towards a really abrupt change. And let's see if the next movie works. I'll just try to illustrate that in the model movie world. And you should be able to see it by eye, because I'm sort of hitting this system with noise, but the ball should be rolling around slower and slower as it's approaching the tipping point. Down at the bottom is an attempt to extract a kind of reliable statistical measure of that slowing down as an early warning signal. So basically, this slowing down of a system before the tipping point could be picked up by a measure here of what's called autocorrelation in time, just the fact that a system becomes more self-similar in time from one time point to the next as it's slowing down. Hopefully that's intuitive. You could also measure what's happening as an increase in variance or standard deviation in the system. But basically, before the tipping point, the fluctuations of the system got longer lived and somewhat higher in amplitude, and we can measure that statistically. Okay, it's not a perfect statistical measure. What you saw was a kind of sliding window moving along the data, and here was an estimate of this, what's called lag 1 autocorrelation in the sliding window, and it's climbing overall, but it doesn't always monotonously go upwards. So we have to do maybe some additional statistical tests to see if we think there's a significant upward trend in the indicator of slowing down. And I'll use that kind of methodology in some examples now. So having thought about the theory, several of us started looking back in Earth history, knowing that there were some abrupt climate change events like the ones we saw in the last ice age, and simply looking at the data before abrupt shifts to see were there these signals of slowing down in the climate system. So here's one example where I cut out the transition here at the end of the Younger Dryas period. The transition, there's an abrupt transition here into the Holocene, if you like, as recorded in Greenland. And this is the depths of the last ice age, the last glacial maximum down here. There's already some fairly funky stuff going on in here. This is the boiling Alarod phase and an abrupt warming at the start. Here is just taking the overall trend line out of the data, and I think it's kind of obvious by eye that there are longer lived centennial fluctuations in the climate system as you near the final end of the ice age that weren't present in the last glacial maximum, where the fluctuations are much shorter lived. There are definitely some problems with this example, you don't really successfully detrend an abrupt shift that's already gone on here. So that influences our statistical indicator. It's climbing anyway before that happens. This is probably a bit of an artifact, but it still climbs afterwards. So there is slowing down in the climate system, or there was before the final kind of termination of the last ice age, as recorded in Greenland. So I sometimes ponder whether if the people then alive then at the time developing the first agriculture actually had these maths techniques, whether they'd have known the end of the ice age was coming. But that's an aside. The other thing we've been doing with many colleagues over the last 10 or so years is then going into model world, where you can obviously force a model to pass a tipping point slowly or quickly, and then you can ask yourself, in model world, are there any early warning signals? So here we're coming solidly back to tipping a collapse of the Atlantic overturning circulation. Here in two different versions of our Gini model. This one has like a simple atmosphere on top of a three-dimensional ocean that has somewhat reduced physics. This has a GCM atmosphere, albeit a low resolution, coupled to the 3D Goldstein ocean that Neil Edwards, Bob Marsh developed. Basically, in this one, we have to add a little bit of noise to the model because it doesn't generate its own weather. This one, all the noise in the strength of the overturning circulation is generated internally in the model by the atmosphere. In both cases, we're forcing the system with some extra fresh water input to the North Atlantic. So eventually the overturning collapses here or here. In this complicated model, there's a time there where the formation of deep water switches off on one side of Greenland, but not the other, in simple terms. When we looked in these models for whether there was a warning signal in these short-lived fluctuations before the collapse, in the simpler model, if we were just looking, say, at the black line, which is this lag1 autocorrelation, in the simpler version of Gini, there's a very robust slowing down signal, which is picked up by that black line going upwards. If you're wondering what all the colour stuff is, it's just checking that this result isn't being influenced by the window length we use or the way we filter the data. In the more complicated model, the pictures may be less clear, but there is certainly a slowing down signal before the first kind of partial collapse of the overturning, and then it gets a lot less clear over here. Then more recently, we got hold of a model called FAMOUS, which is like a low resolution version of another model called HADCM3, which is already kind of old hat to the climate modelers. It was a sort of state-of-the-art model 15 years ago. So it's not a state-of-the-art model anymore, but the good thing about FAMOUS, which is a coupled ocean atmosphere model, I guess, is that you can run it for long enough that you can convince yourself, and others have done this in the literature, that it has two alternative states for the overturning circulation. And you can force it fairly slowly, here over about 1,000 years, again with extra fresh water input, you can force the overturning circulation to collapse. And because it's a fairly, well, it's not high resolution by today's standards, but because it's a fairly resolved three-dimensional model, you can go into the model world and ask yourself, where would be the best place to look for warning signals of a collapse of the overturning circulation? And you can just ask the hypothetical question, what about 26 degrees north, where we already monitor the overturning circulation? Would that be the best place to pick up early warning signals of collapse? Are there early warning signals there? So these are the results at roughly 26 degrees north in the model world. which obviously isn't the real world, but hey, let's have a look. This is the overturning circulation being forced towards a shutdown, which plays out fairly steadily over a couple of hundred years in this model. These are the fluctuations before the collapse, and I think you can just about see by eye, if you get your eye in, that they're slowing down before the collapse is initiated. And sure enough, the autocorrelation in the system is going up, and less convincingly, the variance is going up. So the method sort of seems to be working at 26 degrees north, but the beauty of the complex model is you can look at all latitudes and see what the signals are at all latitudes. So that's what this big colourful mess is. It's like lots of different latitudes colour-coded. This is the overturning strength. This is the autocorrelation trend sort of over time, and this is the variance in the system. And then plotting a kind of percent change in the indicators over here. So it looks like the biggest changes in autocorrelation are near the southern boundary of the Atlantic. The biggest rises in variance are towards the northern boundary. But to do this more properly, we should have some kind of statistical null model to test against. So we basically construct some null models by, we would say, bootstrapping the data. So reorganizing the data in time, but the same data. So you destroy its memory, and that sometimes would give you kind of trends in autocorrelation just by chance, and we want to test statistically against those that null model. So basically that's what we've done at each latitude in the model, and this is another complicated colorful plot, but it shows as a function of latitude and of time, if you like, it turns red when we get a statistically significant early warning signal compared to the null model at that p level, less than 0.05. So what can you take from that? Well, you don't get a reliable early warning signal everywhere. By luck, you can get one at about 26 north, at least for a while. It's more robust at the high northern and southern latitudes, and I think there are physical oceanography reasons for that. Certainly it's kind of blotted out in the tropics because I think other dynamical processes like the wind-driven component of the overturning kind of interfering with the signal. But yeah, if you go to the highest northern latitudes or southern boundary of the Atlantic in this model world, you can get a reliable warning signal of an approaching collapse. If you're a glass half full person, you'll be celebrating the fact that the warning signal is there 200 years in advance of the collapse. But if you're a glass half empty person, you'll note that you need to be monitoring the system for about 500 years before you can pick up a reliable warning. Why is that? Well, that's intuitive. That's because that's kind of the time scale of the longest time scale of the overturning circulation itself. Now that might make you think, oh, this is hopeless. We've only been monitoring at 26 north for like a decade. We're never going to be monitoring for 500 years. But if you're a paleoceanographer in the audience, you probably know that many people are working on reconstructing the strength of the overturning circulation, not just over past centuries, but over past millennia. So I don't think it's hopeless. I actually think it's conceivable. We could reconstruct something about the natural variability and statistical properties of the overturning circulation, and we might conceivably then be able to pick up a signal of whether they're significantly changing due to human activities in a dangerous direction. I want to turn to a slightly different example though, because having played around in models and looking in this past cases of abrupt climate change, we got just about enough confidence that there might be something in these simple methods to start just scanning available climate data and asking ourselves, are there any interesting signals in observational data? Now here, this story is not going to really be about the overturning circulation, but more about shorter term variability in the surface ocean. Although it is intriguing that large areas of the ocean or sea surface temperature data and the fluctuations thereof seem to be slowing down, especially if it's red here. Some areas it's speeding up. Maybe that's what you expect under climate change. You know, some bits of the system slow down, some speed up. But red is the dominant response here, or slowing down of the fluctuations, including, interestingly, in the North Atlantic region, or a lot of it. So there is something I'm working on at the moment. There is a possibility that that might ultimately be tied to the overturning circulation. But let's put that aside for now, because the case study that we've had a proper look at is the North Pacific. because some caveats are required in looking at this diagram, because this is essentially boat thermometer measurements, and as you all know, boats are not as abundant down here, and certainly haven't been trundling around the planet down here for as long or as often as they have in the North Atlantic and the North Pacific. So the data is much better in the North Atlantic and North Pacific sectors. And in the North Pacific, it looks there in red like there's slowing down of the fluctuations in the surface temperature of the North Pacific. And there's a climate index that's kind of built from the pattern of sea surface temperature fluctuations in the North Pacific. It's called the Pacific Decadal Oscillation Index, PDO index. And we were just naively running our methods on these indices. And we came to the PDO index, which is the black thing up there. And we just looked at, was there a slowing down in the fluctuations in that index? And there's an incredibly strong signal of slowing down of fluctuations in this PDO index, which is constructed from kind of North Pacific sea surface temperatures. The slowing down signal here is incredibly robust in a statistical sense when you test it against a null model there. Very strong rising autocorrelation of the fluctuations, then the variance going up but then doing something a bit different. And we scratched our heads and we thought, well, maybe this is some kind of artifact. Maybe it's something to do with how the data would have been infilled more further back in the past. So then we went back to the raw data underneath this index. We looked at had some partly infilled data that's called HAD-ISST, and just aggregated that over the whole North Pacific and found the slowing down signal was present for the whole North Pacific in that data set. Then we went back to the raw HAD-SST3 data, and this is over a shorter time interval now, because basically there weren't so many boats taking measurements before the Second World War, so we're just looking after World War II. But even so, for the whole North Pacific, aggregated there's a strong slowing down of the temperature fluctuations and increasing variance, which took me by surprise for sure. And then we saw, can we explain that? Is there something really simple going on in the climate system that might explain that? So a possible simple explanation that has got nothing to do with tipping points would just be maybe the surface ocean layer is getting thicker, so it's a bigger volume of water and therefore it has a bigger heat capacity. So if you change its temperature, any fluctuation in temperature is going to take longer to decay if the heat capacity is larger. And that would work if we could convince ourselves that the mixed layer was getting systematically deeper in the North Pacific. And as I'm sure some of you know better than me, there is a climatology for mixed layer depth. It's very patchy, but it's there. And there is some signal of mixed layer deepening, at least since the 1960s in the North Pacific, and interestingly, even more so in the North Atlantic. So following a very famous and now 40-year-old model, yeah, if the mixed layer depth goes up and the heat capacity of the system goes up, if there are, let's assume we've looked at it and there aren't any great changes in wind speed in this region, at least not on the average, although there are interesting shorter term variations, then yeah, if the mixed layer goes up and that term gets smaller, this alpha, the autocorrelation of the system should get larger, fluctuations should slow down. So we basically went into the data and looked by grid cell with this model and said, could we use this simple model and the observed changes in mixed layer depth to explain the slowing down signal? And that's what this thing here is. Basically, these are the observed mixed layer depth changes. They're typically order of 10 to 20 meters, sometimes 30 meter increase in mixed layer depth from 1960 there to 2006. These are the changes that would be required, assuming that simple model, in order to get the observed slowing down. And in quite a lot of the North Pacific, it could be the explanation, basically. But the bits I've highlighted with the dark outlining are telling us that there are parts of the North Pacific where there's really strong slowing down of surface temperature fluctuations that can't just be explained by the known deepening of the mixed layer. So I'm going to have to leave that there because I haven't worked out why those physical climate changes are happening. But for the more biologically minded in the audience, this is kind of important and interesting because the North Pacific, especially over here, is a place famous for there having been regime shifts or abrupt shifts in fisheries catches around 76, 77 and in the early 90s in particular. So there have been abrupt changes definitely in the ecosystem in this region. So we got curious as to whether this very marked trend in the physical environment of the ecosystem, the slowing down of the temperature fluctuations, could have something to do with that. And in a nutshell, the answer is it could, because you can think of the marine ecosystem as kind of integrating this ocean temperature variability and having its own kind of timescale, which is often in the models assumed to be tied to a reproductive timescale for the zooplankton component. And I'm not sure if this is right, but is often discussed as being around a 2-year timescale for the ecosystem. Whereas, at least back in the 1960s, the typical recovery timescale of the ocean's fluctuations of temperature was quicker than that, more like half a year. But if the ocean's variability or the temperature fluctuations are slowing down, then they're coming towards the timescale of the ecosystem if it's assumed to be fixed or given by some kind of reproductive timescale there. And in a simple model, or two different simple models that we played with, basically when we force these simple ecosystem models with the slowing down of the ocean variability, then the ecosystem models become more correlated with the ocean variability and they show greater amplitude fluctuations. And that's true even if you normalize out any changes in amplitude of the ocean variability. So you keep the slowing down of the fluctuations, but you normalize out the amplitude of them. Even then, you get a very marked increase in amplitude of the ecosystem fluctuations. And then you can debate whether you believe the ecosystem itself has tipping points or not. That result holds in a model where it doesn't have tipping points and in a model where it does. But if you believe the ecosystem has got tipping points, then they become more likely to be crossed as the ocean variability slows down. Because it's a bit like giving the ecosystem bigger and more persistent shoves. Or even if you normalize out the size of the shoves, if they're more persistent shoves, it still becomes more likely that you tip the ecosystem. So in a nutshell, I'm saying that maybe this signal that's in the physical climate of the North Pacific could have something to do with the fact that in the late 20th century there were some marked abrupt changes in the ecosystem. Haha, I hopefully left myself just enough time then to change gear and step back a bit then and say, okay, maybe I've convinced you that there could be some approaching tipping points in the climate, that they might get more likely as the temperature goes up. What should that be doing to our kind of collective activity or not on the climate change problem? So climate, it's kind of obvious what the answer should be, right? But let's try and sort of formally show what the answer should be. So in this game of climate economics, there are simple things called integrated assessment models, where economists consider how do the costs of tackling climate change vary as a function of the global temperature change you're trying to achieve. And the lower you want to hold the temperature, the more money you've got to spend to mitigate fossil fuel emissions, put in alternative energy systems, etc., is the general assumption. Equally, as the temperature goes up, there's expected to be some increase in the damages from climate change. No one's really sure what shape that takes, but your typical integrated assessment model assumes it's a quadratic function of temperature. But the typical model assumes that is perfectly known, it's deterministic, we know perfectly both the costs of mitigation and the costs of damages, and all we have to do is like a really simple optimization, and that's literally what goes on in these integrated assessment models, albeit kind of iterated over time. So I'm really curious, well, what if you acknowledge that the real world has got uncertainty, including the possibility of uncertain abrupt changes, which might turn into abrupt jumps in the damage function there. Maybe it steps up at some point that we're not quite sure where that point is. How should that affect the optimal policy, as the economists would call it? So their models have in them a sort of crude carbon cycle and climate and an economic component, which is like a global a welfare function, or almost like a GDP function. And there's this mystery figure, an omniscient social planner, a sort of godlike figure who can set consumption levels in the global economy and choose whether or not to mitigate fossil fuel emissions here, which affect the carbon cycle. And the standard model in the middle is just deterministic. We added on a stochastic possibility of tipping points. And then we have to change the nature of the model somewhat, because it's now got this stochastic or somewhat random component in it. So we have to solve it in a different way. But we're really curious, what would that do to the results? And in the most recent work, we've been putting in more than one tipping point as a possibility. We've been going back to that expert elicitation I talked about earlier. And in the elicitation, there was some causal information extracted from the experts about, if I tip this bit of the climate system, how likely or not does that affect the probability of tipping some other bit? So if we just zoned in here on the Atlantic thermohaline circulation, a long observed thing is that if the Greenland ice sheet's already melting, that's a source of fresh water to the regions of deep convection around Greenland that increases the likelihood of collapsing the overturning. Maybe doesn't increase it a lot, but it's going to be increasing it rather than decreasing it. However, if we collapse the overturning circulation first, we'd have less transport of heat up to Greenland, and it would reduce the likelihood of tipping a meltdown of Greenland, for example. Lots of connections in the diagram, but we had to go at putting in some of those interactions. So to make this a half reasonable model, we need to make some heroic assumptions, as ever, assign some both probabilities of tipping the different systems, which we'll get from the elicitation, some timescales over which they tip, some final magnitudes of the damages. The most uncertain thing here, by the way, is how damaging would these events be to the global economy. Think of it like that. Nobody knows, I think. But there are papers in the literature and work saying that a collapse of the overturning circulation would give a 25% permanent reduction in global GDP, which would be like the Great Depression in the 20s and 30s, but permanent. We've been more conservative. We went with like a 10 to 20% range and a 15% guess hit on GDP. Anyway, you chuck all that in the model, you go from the kind of grey line down here up to the black line with the uncertainty range on it. So the headline results are perhaps intuitively obvious, but you jump from a low incentive to control emissions to an immediate compulsion because of the possibility of future tipping points to really ramp up your mitigation efforts and max them out by 2050, which means shutting down fossil fuel burning by 2050, which in this model world holds the temperature under 1.5 degrees of warming. So it meets the kind of Paris Agreement climate target. So that's a radical shift from what the standard model was doing, which was drifting on up to 3 and more degrees of warming next century. And if you're curious, you can go into that model world and look at instances of it where things get tipped in different orders and learn some other funky stuff. Like if by chance we convinced ourselves we'd passed a threshold for melting the Greenland ice sheet, suddenly efforts to mitigate, expressed here as the price of carbon emissions, would jump up radically because of the assumption that that makes a tipping of the Atlantic overturning more likely, and it in turn is very damaging. So let's finish there. Hopefully I told you something interesting about how tipping points could, if we just carry on business as usual, become high impact, high probability events, that there are some early warning methods for them. That interestingly, the temperature fluctuations in the North Pacific have already slowed down, and that might have played a role in past marine ecosystem regime shifts. I think we could conceivably develop some tipping point warning systems, certainly for the slow parts of the climate, like the ocean overturning, and that the threat of these possible interacting tipping points ought to be radically changing how we view the climate problem. And basically, we should be setting a much higher price now on greenhouse gas emissions, especially carbon dioxide, and working much harder than we are to tackle the causes of climate change. Thank you.